right, welcome to the Ph.D. defense of Jun Zhong. He got a degree in engineering mechanics at Hunan University, a bachelor's degree in 2012, and then stayed on to get a master's in solid mechanics. Then he joined my lab in 2015. I had a new project with Dr. Laurie Virgin, who's at Duke, where we needed someone who knew some solid mechanics, but could also do some dynamical systems theory and Hamiltonian systems. And Jun was, he had a good background in solid mechanics and was willing to learn the dynamical systems necessary. So he's going to be talking about that today. He's my most prolific student in terms of writing papers. He's got 13 journal publications, not all with me, and 2 more on the way. He's very prolific. He's got a postdoc lined up after he leaves. And we're going to miss him. But without further ado, go ahead, Jun.
Thank you for the introduction, and thank you all for coming to my defense. And first, thank Dr. Ross for accepting me as a researcher in the group, and I learned a lot here. Let me start the presentation. And as you can see from the title, my study is about escape dynamics, but probably most of you do not know what it is. Here I will briefly give you some examples about what escape dynamics is. The first one is the shadow arch, or not shadows. So like this one, this is our bucket beam, and the escape means the transition from one stable configuration to the other configuration. And for a 2-mode truncation, the system is a 2-degree Braided system. On the right figure, it is a potential contour. There are 2 potential wells. The escape means the motion between W1 and W2 usually occur around the saddle point. And then it is the flip over of the umbrella. Probably don't be scared. So it is multi-stable. And an equivalent system is like the jumping hover. And then you can, the capsize of shift motion and chemical reaction and 3-body power like this multi-body powers. And then there are some toys you can see. And for studying the escape dynamics, sometimes we use a framework from tube dynamics. What's that? For example, there we consider 2 potential wells A and B. In general, the potential wells are connected by the rack 1 saddle here. Around the saddle, there is an unstable periodic orbit. The periodic orbit has an unstable and stable invariant manifold, and all the transition between A and B must occur inside of the tube. The tube is the invariant manifold. We call it transition tube, and we will use the same name in the next topic. In my study, in general, I consider 2 forces. One is dissipative force, and the other one is gyroscopic force. For dissipative force, I just consider the linear viscous damping. If we consider the damping, the phase-space structure is different. So we don't have constant motion, then we don't have periodic orbit. So we need to develop some new methods to construct, to compute the transition boundary. Then for the gyroscopic force, why we are interested in this kind of system? Because the gyroscopic system has some very interesting phenomena. The first one is the unstable motion can be stabilized. For example, a rolling ball on the surface, on a saddle surface, the motion is unstable, but if we rotate the surface, we have the gyroscopic forces, and the unstable motion can be stable. And then, if we introduce our dissipation to such system, the stable motion is unstable. no matter how small the dissipation is. So the first topic I want to study the effect of dissipative and gyroscopic forces on the transition. This is a rolling ball on a stationary surface. The ball is moving on the surface. There are 4 potential wells. Because of the dissipation of energy, the ball will finally stop at this potential well. As I mentioned, in general, the motion between the potential wells will occur around the saddle here. So for the first topic, we want to study the linearized dynamics around the saddle to review some basic idea. In this case, we can go to the nonlinear case. For the equations of motion, we use the Hamiltonian approach. First, we obtain the Hamiltonian function, and then use the Hamiltonian equations to obtain the equation of motion. Then, here, Qi is the external force. If we consider the conservative system, I mean the Qi is 0, we have some constant of motion. This is one reason why we use Hamiltonian system. And the other one advantage is we can directly obtain the equations of motion by the first order. So we don't need to introduce other variables. For the linearization about the saddle, it has 4 eigenvalues, 1 pair of real number and a pair of imaginary numbers. These are the 4 eigenvectors. So this saddle is of type saddle plus center. If we introduce some change of variable here, by using the generalized eigenvectors, we can transfer the phase space to the eigenspace. This is the Hamiltonian normal form, and then this is the quadratic Hamiltonian. We can obtain the analytical solution in eigenspace. This is the flow in eigenspace. It is a saddle plus center, and they uncoupled. The left one is the saddle projection, and the right one is the center projection. So here you might be wondering, how do we interpret the transition by using the saddle and center projections? Here, let me introduce the saddle projection. Here we select 2 boundary lines, N1 and N2. If one trajectory starts from N1 and then can reach V2, we can consider this trajectory can escape from the potential well, because this is the equilibrium point. This boundary line is on one side of the saddle, and this is on the other side of the saddle. If one trajectory starts from N1 and then return to N1 itself, we can consider it as non-transit orbit, so it cannot escape from the potential well. Here, in saddle projection, we have 4 types of trajectories. The first one is periodic orbit, which is the origin in saddle projection and the harmonic oscillation in center projection. And then we have 2 types of asymptotic orbits. The first type is stable. They are gradually approaching to the periodic orbit. And then these 2 are the unstable asymptotic orbit. They are leaving the periodic orbit. And then we have 2 transit orbit and 2 non-transit orbit. Here, I should mention the fastest trajectory. This concept, I will use it later. This is the fastest trajectory. It has the best velocity, so it has the largest possibility to escape. Here, this is the asymptotic orbit. What I study here is I want to find this region. This region is for the transition. All the transit orbit must have the initial conditions within this area or here. Because this is a forward transition, this is backward transition. Here you can notice, in fact, the center projection, it doesn't affect the transition. It just takes up some energy. So in the linearized dynamics, we just need to consider the saddle projection and to find the stable manifold. So this is the boundary controlling the transition. Then this is the flow in eigenspace of the dissipative system. here, because we consider the energy dissipation, we don't have periodic orbit. So here the origin becomes the focus type asymptotic orbit, and it is starting from the boundary and then gradually approaching to the origin in the focus projection. Then we have stable asymptotic orbit and unstable asymptotic orbit and transit orbit and non-transit orbit. Here, the difference between the dissipative system and the conservative system is here the stable asymptotic orbit and unstable asymptotic orbit, they are tilted compared with the conservative system. And also, so this area for the transition is smaller than conservative system. Then I discuss the flow in phase space of the conservative system. Because first I studied the linearized dynamics, I can obtain the analytical solutions. Here, this is the solution for the conservative system. This part, the first term is the unstable term, and this term is the stable term. This is a harmonic oscillation term. Then, because we want to obtain the stable asymptotic orbit, we just need to set the unstable term at 0. So we can obtain the stable asymptotic orbit. We have this form. Here I just set Q10 as 0. Finally, I can obtain Q20, P10, and P20 in terms of QY0, PX0, and PY0. Finally, I can substitute them to the quadratic Hamiltonian in the eigenspace. Then I can solve for the stable asymptotic orbit. And this is the flow in the phase space. Here is the transition tube I mentioned earlier. As I mentioned, all the transition or the escape from the potential waves can just occur inside of the transition tube. It means all the transit orbits, they must have the initial conditions inside of the transition tube. And here we have another very important concept. It's called the critical surface. The critical surface, it cuts the transition tube into two parts. The left part gives the initial conditions for the trajectories which start from left and then transition to the right. And vice versa for the right part. And also for the periodic orbit, it's moving on the critical surface. So the way I obtain the critical surface is computing the periodic orbit. In this case, the transit orbit, it can cross the critical surface, and non-transit orbit, it will bounce back before it reaches to the critical surface, and absolutely the asymptotic orbit, they will gradually approach to the critical surface. Here, I want to mention two behaviors. The first one is the transition tube for the linearized dynamics is parallel to the position space. Here is the position space. I will discuss it later. For the critical surface, it is vertical to the position space. Here, in order to show how the transition tube works, I select a Poincare section here, and this is the transition boundary on the Poincare section. I select 3 points. One is outside, one is inside, and one is on the boundary. After I integrate forward, I can obtain non-transit orbit, transit orbit, and asymptotic orbit. So here it shows the result I obtained here is right. Then I show the flow in phase space of the dissipative system. Here, the transition tube becomes ellipsoid. Why we have ellipsoid? Here, ellipsoid has 2 bounding points. This is the farthest point the trajectory can start. How do we interpret this behavior? For example, we consider a ball moving on the surface. And here, in fact, this is a contour of the arch. I didn't mention it before. If we start far from the saddle point, the energy probably will become smaller than the energy of the saddle. So the potential surface will be closed. So this ball cannot escape from the potential well. And then I think you can try a little bit. Yeah. So this is the reason why we have ellipsoid. Here we still have the critical surface, but we don't have periodic orbit. Instead, we have focus type asymptotic orbit. It is moving on the critical surface and gradually approaching to the equilibrium point in the center. Then I select the same punctuate section. I can obtain a smaller transition boundary on the punctuate section. Here, the dashed curve is for the conservative system. They have the same energy, so we can know that dissipation makes the transition boundary smaller when we consider the dissipation. Then I consider the flow in the position space. I just need to project the phase space to the position space x and y. Here, the shadow area is the zero velocity curve. All the motion, all the possible motion can just occur inside of this area. This is the boundary of all possible motion. And in the center, this is a periodic orbit. Is a projection of the transition tube. So keep in mind, all the possible transition must be inside of the strip, but it is not enough in the position space. We have another factor which is called the wedge of velocity. It controls the direction. For example, if the ball wants to transit to the potential well over that direction, the direction must be right. So here the wedge controls the right direction. These are the transit orbit. They are inside of the wedge of velocity, and non-transit orbit, and one asymptotic orbit, and another asymptotic orbit. In fact, you can notice the boundary of the wedge is the lower and upper bound of the transition boundary at a specific point y. This is the flow in the dissipative system. Here we have ellipse of transition. It is the projection of the transition ellipsoid. Here we still have the same wedge, but the size of the wedge for the dissipative system is smaller than the conservative system. Then I want to study the gyroscopic forces. And as I mentioned, we can just make the surface rotating. Then I can introduce the gyroscopic force. Since the system is rotating, I need to use the rotating frame to get the equations of motion. This is the phase space in the conservative system. I have very similar structure which controls the transition, but because it is similar, I don't give much details. But here I want to talk about two differences. Here, the transition tube here it is not parallel to the position space. Also, the critical surface is not perpendicular to the position space. And there are two strips. I will discuss it later. For the dissipative system, we also have a very similar structure. But here on the punctuate section, the transition boundary is not a standard ellipse. It is not vertical or perpendicular to the y-axis. This is the flow in the position space for the conservative system. Here, the difference between the non-gyroscopic system and gyroscopic system is here. We have two strips. This one gives the boundary of the stable asymptotic orbit. This one gives the strip for the unstable asymptotic orbit. And also this is the periodic orbit. It is not a segment like before. It is an ellipse. So from here you can know the gyroscopic force system is very interesting. Then I have the dissipative system. Very similar figure as before. For this topic, it has been finished and published in Nonlinear Science and Numeric Simulation, and this is article information. since I have studied the linearized dynamics around the saddle, I want to extend it to the nonlinear system to find the nonlinear structures that control the transition. For the nonlinear system, I want to use the subflow of a shallow arch. This is the force and displacement relation. If we apply our force to the arch and increase the force to the point C, if we keep increasing the force, the arch will directly jump to the other stable configuration. For example, like point D. But if the arch is not shallow, here for the shallow arch problem, it is pitchfork bifurcation. But if the arch is not shallow, it is a saddle load bifurcation. For pitchfork bifurcation, the deformation is asymmetric, is symmetric. But for the for the saddle load bifurcation, it is symmetric. But for pitchfork, it is asymmetric. Here, in my study, I want to introduce some initial imperfection of the arch. So the deformation is asymmetric. To capture the asymmetric deformation, I introduce two mode shape truncation, x and y. X and y are the amplitudes in the first and second order mode shape. After I introduce the two mode shape truncation, I have a 2-degree of freedom system. The left one, I didn't consider the initial imperfection. This is the potential contour. As I mentioned, there are two potential wells, W1 and W2, and S1 and S2 are the rank 1 saddle, and H is a hilltop, it is a rank 2 saddle. In general, S1 and S2 have lower energy than H, so in general, the escape will occur around this area or this area. In this one, I consider the initial imperfection. So the contour, the symmetry is broken for both x direction and y direction. And for the parameters and geometry I considered in the study, S1 has lower energy than S2. So the trajectory sometimes escape from the potential well most probably around S1. Since I have studied the linearized dynamics for the rolling ball problem, they share very similar behavior, so I don't talk about the linearized dynamics for the shallow arch here. I just directly jump to the nonlinear case. For linearized dynamics, we can obtain the analytical solution, but for nonlinear case, it is very hard. Sometimes we use numeric solution. Here, I select two puncture sections on potential well W1 and potential well W2, and in the center it is periodic orbit. This is the transition boundary on one puncture section obtained by the linearized dynamics. But in general, it is not the true boundary for the nonlinear system. For example, the nonlinear system, the boundary is like this. They have some difference. How do we obtain the boundary for the nonlinear system? I developed our bisection method. I used the idea of bisection method. For example, I select one point inside of the boundary, and then select one direction, select one point outside of the boundary. I can select their middle point and integrate in the nonlinear system forward in time, and I can know this is transit orbit. So I can select point 3 as the inner point, and then select the middle point, middle point, middle point. Finally, I can obtain the boundary along this direction, and I can select another direction and the boundary. So finally, I can obtain the boundary for the nonlinear case. This is the transition tube for the nonlinear system in the conservative system. This is a projection onto the position space. And in the linearized system, the strip is straight, but here the strip is curved. And I gave two concrete sections. In fact, you can know the direction of the flow of the transition tube. It is a stable invariant manifold and the unstable invariant manifold. But in this topic, I didn't use any concept of invariant manifold. Because the energy keeps constant, the cross-section of the transition tube here and here are equal. Then I give the dissipative system. Here, the difference is I just obtained the transition boundary on this concrete section, and then I obtain a lot of initial conditions on the boundary, and I integrate forward in time, so I can obtain a tube here. And you can notice here, around the saddle, the size of the tube shrinks dramatically. Why we have this behavior? Because they are almost the asymptotic orbits, or we can say they are asymptotic orbit. So they will move around the saddle for several times, traveling long distance. So the trajectories will lose a lot of energy. So this is the reason why the size shrinks dramatically. I give some examples about the trajectories. This is the transition boundary on the concrete section. The outer one is for the conservative system, and the inner one is for the dissipative system. First, I consider the conservative system. I select point A and point B and integrate forward. I can obtain two trajectories. A, because it is outside of the boundary, so it is a non-transit orbit. And B is inside of the boundary, so it is transit orbit. Then I do the same for the dissipative system, selecting point B and point C. We can say point B is non-transit orbit, and point C is transit orbit. Then we consider the same initial condition, point B, for both conservative system and dissipative system. We can know in conservative system it is a transit orbit, but in dissipative system it is a non-transit orbit. It means the dissipation sometimes will reduce the possibility of transition. It can make a transit orbit become a non-transit orbit. This paper has been published in International Journal of Mechanical Sciences, and this is article information. As I mentioned, the transition boundary is the stable and unstable invariant manifold, but in second topic, even I have studied the nonlinear system, but I didn't use any information about the invariant manifold. So in the next topic, I want to use the concept of invariant manifold to study the transition boundary. For the invariant manifold, for dissipative system and conservative system, they are different. How to say that? For the conservative system, the invariant manifold is a periodic orbit, but in the dissipative system, the invariant manifold is the rank 1 saddle. So to obtain different kinds of invariant manifold, we have different ideas and different algorithms. Let me introduce them one by one. For the conservative system, the computation about the invariant manifold of the periodic orbit, we have two steps. The first one is computing the periodic orbit. We have several methods used in our group. The first one is the differential correction and continuation. I didn't use this algorithm, but Dr. Ross used very often in his study. And then the bisection method developed in the second topic is still working. But here, I want to use BVP approach because the system is very complicated, and BVP approach can control the end point of one trajectory, which can be controllable and efficient and fast. After we obtain the periodic orbit, we can globalize the invariant manifold obtained from the linearized dynamics. The algorithm to compute the periodic orbit, we can solve a proper boundary value problem. First, let us consider a dynamic system written by this form. because we want to use BVP approach, we need to have a specific domain. So we need to rescale the time. Here we introduce capital T. So tau now becomes the time, and it can vary from 1 to 0. For our specific periodic orbit, we have this boundary condition. It means the periodic orbit starting from one point, after one period, it will return to the point where it starts. So this is a closed, closed situation. But you know, all the points on the periodic orbit have the same situation, have the same relation. We have this behavior is called the phase shift. So we need to give one more phase condition to fix the fixed point. We use the orthogonal condition. Here, x star is the periodic orbit we have obtained. And then this is the tangent direction. So this is the right reason why it's called orthogonal condition. This algorithm will be implemented in the MATLAB-based packaging. The packaging has already write down all of the process, so I just need to directly use the packages there. And then for the globalization of the manifold, first we need to obtain the Manodromy matrix. Its eigenvalues, it has 4 eigenvalues. Lambda 1 is bigger than 1, and lambda 2 is smaller than 1. Lambda 3 and lambda 4 are equal to 1 because we have periodic orbit in the conservative system. Then how to obtain the Manodromy matrix? We can first obtain the state transition matrix, which can be obtained from the variational equation, from the equations of motion. And this is the initial condition. After we obtain phi t, we can obtain the Manodromy matrix. Then we denote the stable and unstable eigenvectors of the Manodromy matrix by Ys and Yu at point x0. Then we can obtain the initial case for the invariant manifold at point x0. Then we use these initial conditions and integrate in the nonlinear system forward or backward in time. We can obtain the manifold at that point. Then for other points on the periodic orbit, we have this relation to transfer to obtain other stable and unstable directions. This is the same transition tube but obtained by the BVP approach. Here I give the 2 concrete sections. The results are from both Bisection method and COCO. They match very well. For the invariant manifold of equilibrium point, here I'm in the rank 1 saddle. I consider the same system. This system, we denote the equilibrium point as xe. Its Jacobian has k eigenvalues, lambda I with the negative real part. So we have corresponding eigenvectors denoted by vi. For this system, the equilibrium point has a k-dimensional local invariant stable manifold, and then the local invariant manifold is tangent to the stable subspace Es of the linearized system. And we can globalize the linearized invariant manifold to obtain the global invariant manifold. I will use BVP approach again. For the system here, first I use the shallow arch as an example to show the process. Here the first 4 equations are Hamiltonian equations. X and Y are the position and Px, Py are the momentum. Ch is the linear viscous damping. And here why we have the 5th equation? Because for different trajectories, they have different time. So its derivative with respect to time is 0. So I have this equation. And I have some boundary conditions. The first one is selected from an initial sphere in the stable subspace of the linearized system. S is the boundary conditions at at tau equals 0. And then, because we just care about specific energy, so it is meaningful to study the transition. We need to fix the energy at point tau equals 1. Here we have two, I want to introduce more details about the initial sphere. Here, the radius of the initial sphere is R0, and V1, V2, V3 are three stable eigenvectors because this system has three stable invariant manifolds. And theta and phi are the parameters which can it means we can change the direction of the three stable eigenvectors. So theta and phi are two free parameters. In this case, we have three variables, x, y, px, py, and t. Then we have two parameters, phi and theta, minus 5 boundary conditions. So this problem is a two-parameter continuation. It means we do the continuation on the surface. In fact, we do the continuation on the ellipsoid. But sometimes, it is very difficult to do the two-parameter continuation. We want to reduce the problem to one-parameter continuation. In this case, we can introduce one Bisection as before. Here, I want to remind one concept. It is the fastest trajectory. Here, as I mentioned, the fastest trajectory, it just has the saddle projection. And then it has the best velocity, so it has the largest possibility to escape from the potential well. Here, this is the initial sphere, and this is the equilibrium point. This is the initial condition for the fastest trajectory. After integrate the nonlinear equations backward in time until we have the energy equal to h. So this is the end point. In fact, this is the end point of the nonlinear transition ellipsoid. Then we can select a lot of points on the fastest trajectory and obtain the tangent vectors. So the Bisection are the plane normal to the tangent vector at each point. We can do the continuation on the Bisection. Here I introduce how to do the continuation on the Bisection. Here, this is y and py plane. This is the true boundary we obtained on the Bisection. This is the fastest trajectory. In general, it has the energy lower than the energy we want. So this is inside of the boundary. So we want to do the continuation to reach the energy we want on the Bisection. Here we can fix py and do the continuation along y direction until it reaches the energy we want. So this is this point we obtain. And then we can do the continuation along the boundary. So this is the boundary. Here I showed you some nonlinear transition ellipsoid with different energy. The left two are in phase space, and the right two are in the position space. And this is smaller energy, this is bigger energy. Here we can notice the size of the transition ellipsoid. For bigger energy, the transition ellipsoid is bigger than the smaller energy. Then you might be wondering, I consider the dissipative system, why I have periodic orbit. Here we don't have periodic orbit. I just compute the periodic orbit, and in fact, it gives all of the initial conditions for the focus type asymptotic orbit. So this is the critical surface for the nonlinear system. And the periodic orbit, in fact, is the largest cross-section for the transition ellipsoid. Here, I want to show the video. Application, the degree of fitting system for physical problems are much higher, so we can consider the higher degree of fitting system, but it should be very difficult. And then we can consider the two-parameter continuation. Even this is very hard, but once we finish this idea, I think it will push forward our study very dramatically. And then for the experiments, Dr. Virgin is collaborating with us doing the experiments, but they have finished the rolling ball experiments. The result matches very well with the theory, but my idea is we can finish the experiment about the shallow arch problem. It couldn't be better. I think Dr. Ross and Dr. Virgin will have some ideas about the experiments in the future. Finally, I want to acknowledge a lot of people. First of all, I want to thank Dr. Ross for the long-term supporting. And whenever I have concerns or problems, he is always there helping me.
All right. Thank you, Jun.